Hey, let's try to define a deep perceptron to model the XOR gate, and we're going to do it first in a very simple way. So this is basically the truth table of the XOR. I'm going to show you now that the, the XOR gate can be modeled with a combination of different Boolean gates. And in particular, now let's consider this combination here, in which here we have the OR gate, here we have the not AND gate, and they receive both the input, the binary input x1 and x2. And then here there will be an output from both gates. Here we call it Z1 and Z2. That is going to go through another Boolean gate, which is the AND gate. And the output Y, I claim I claim that the system here is the equivalent to basically to the XOR gate. So this is basically the system equivalent to the XOR gate. And in formulas, this model is going to be Z1 equal to the OR of x1, x2, Z2 equal to the not AND of x1 and x2, and then the output of this first layer of Boolean gates. This is a layer of Boolean gates. The output, it will be the input of this AND Boolean gate. And we already have seen that each of these single Boolean gates can be modeled with a linear perceptron. And so we see that this basically is a network of perceptrons made of one layer. There is an hidden layer which then output to one single perceptron. And indeed, let's see now that if this system of Boolean gates, it is really the XOR gate. To do that, now we're going to do another table here, in which I'll do it here. So we have the input x1 and x2. Then we'll have the two outputs, Z1 and Z2, and then the Y output of the last layer. Okay, and basically we still have 1 and 1 minus 1 and 1, 1 minus 1 minus 1 and minus 1. Okay, and so let's see what is remember that Z1 is gonna be this is gonna be the output of an OR gate. This is gonna be the output of a not AND gate, and this is gonna be the output of an AND gate. Okay, just to remember so what happened, the OR gate applied to these four pairs, we're gonna get true, 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 and false. The not AND of the same pair is going to be the negation of and, and so here is going to give us -1, because we have both true and true. Here it will be positive, +1. Here is also going to be +1. And also here is going to be +1. So remember, this is the negation of the AND gate. And then we have to do the AND gate Boolean operator applied to these inputs here. So this is going to give us 1 and -1 is going to give us -1 because it's the AND. Plus 1 plus 1 is going to give you +1. It's going to give us 1. It's going to give us -1. So as you can see, we match the outputs are the same. So basically, this system of Boolean gates is it is the XOR gate. It models the XOR gate. But we also know that each of these Boolean gates can be defined, can be formulated as linear perceptrons. What does that mean? That I can find a weight W1 and a bias B1. Here I can find weights W2 and B2 to model the not end, and here I can also find a third set of weights and bias to model the three gates. And this we know how to do it. I made a video about it, so just find it in this YouTube videos, in the YouTube playlist. And so basically now we have that this can also be written as the sign of W1 dotted X plus B1, the sign of W2 dotted X plus B2, and this like the sign of W3 dotted Z plus B3. So let me remind you that here we have our input vector x1 and x2, and the output of the first layer, it is basically given by this Z1 and Z2. So actually what we have here, here we have a model of a one layer perceptron. Obviously, a one layer neural network. Or the deep perceptron, or the multi-layer multi-perceptron. And what happened is because we have this hidden layer between the input and the output, there is this hidden layer which does this intermediate operation before going to the final perceptron here. And let's understand, geometrically what happened here. Why basically, I cannot model the XOR operator with just one linear perceptron. We already know why. We're gonna revisit it again. And let's understand why instead this neural network, in which has one layer of hidden perceptrons, instead can succeed in modeling the XOR gate. And to do that, we will need this okay. So this is the true table of our deep perceptron, or system of Boolean gates. And what I'm going to do now, geometrically, also, let's plot the here basically we have the input space x1 and x2. And then after the input, this input goes through the first layer. And there will be an intermediate output given by two numbers, Z1 and Z2. And this is called basically, these are the latent variables, which they form, this is basically the input space. And here we will have our latent space. Okay, and so now let's plot in the input space. We know that the inputs data are basically given by, we have 4 pairs, right? Plus a label corresponding to their outcome, to their output. And, 1 and 1, which correspond to false results as an outcome, false. Then we have -1, -1, and 1. It is a true result, which I'm going to keep it empty. Then we have 1 and -1, which has a true outcome, a true output, the Y. And then we have -1 and -1, which correspond to a false results, okay? And here I'm plotting, here representing with this false, this is true. Okay, and these are the outcomes of the XOR, of the final output. Okay, so just and then what happened that this input goes through the first layer of neurons, of the perceptrons, the OR and the NAND, and they give us a new pair of outputs, which are basically Z1 and Z2. So, quindi, for example, let's start with the first pair. 1 and 1 is basically this. And after it goes through the first layer of neurons, we get this output, 1 and -1. So 1 and -1. So 1 and -1, 1 and -1. So what happened is that 1 and -1. This point, it is mapped down here. Okay? 1 and -1. Then let's look at the second pair. Let's look at this pair. -1 and 1 -1 and 1, it is this. And -1 and 1, it is mapped in 1, 1, which is basically here. So we get that this is mapped here. Okay? Then let's look at this. 1 and -1, 1 and -1, it is this. And it is mapped also in the same point, 1, 1. And then the last one, -1 and 1, which is here. It is mapped to -1 plus 1. -1 plus 1. It is mapped up here. So this basically is going to go here. So Winnie, you can see that what the hidden layer does, it basically transform the input space, and by pulling and moving around the data points and reorder them in such a way that now we can do a linear classification of the true results from the false results. You see, now in the latent space, I can do a linear, I can use a linear perceptron, which is basically the AND gate. To classify correctly the XOR operator. So now we see that the importance of this hidden layer is to basically rearrange, transform the initial data points and reshuffling in space in such a way that then they can be nicely classified with a linear perceptron with a binary classification. And that's basically, the power of deep neural networks. So the effect of each layer is to basically rearrange, transform the original data points and move them and stretch them, compress them in such a way to allow an easy classification of the data. So what I'm going to do now, I'm going to switch to, I'm going to share, I'm going to share the screen. And we are going to run, I'm going to show you, this is basically the Python code that model a linear perceptron. And you see that here the input data are the one for a XOR gate. It's easy to recognize it because here we have 1 and 1 correspond to -1. So then, we go through an initialization of the weights and bias randomly, a learning rate of 0.1, number of epochs 30. Then here there is the training loop that we have studied in previous videos. And then there is some plotting, testing and plotting. So let's see how it does let me delete the output and start all over. Let's run it. So you see that there are 30 epochs. So initially now we have this random bias here, weights and bias, and they they converge, the training algorithm converge to something, but the error did not go to zero. So there is a constant error. And indeed, as you can see, no, the the perceptron is not able to match the expected outputs. So, it doesn't work. And why? Because, I mean, there is no way to separate with just one line the true results from the false results. In order to do that, we need a multi-perceptron, which is this. And now here for the multi-perceptron, I'm using the sigmoid function. Instead, the activation function, I'm using the sigmoid function instead of the sine function. And for example, now the XOR data, I can even model them with 0 and 1 or instead of -1 and 1. So the same things. Now what happened that we have to do initialization of 3 perceptrons. These are the 2 perceptrons of the first layer, and this is then the final layer perceptron is only 1. And we will need a little bit of more epochs to get convergence. And then here there is all the training loop, which loops over the epochs and then over all the data points, and is basically using least square to minimize to update the weights. And this is done to a gradient descent algorithm that uses back propagation in order to compute the derivatives the derivative with respect to the parameters, which are basically here. And so this is the update of the network to the training to find the weights and biases. And then there is some plotting in the input space and latent space. So let's see what let's see how the model does. So you see that it took roughly 2,000 iterations, 2,000 epochs, to get to a very, very, very small error. And you can see that, the multi-layer perceptron does pretty well, so is able to reproduce, to recover to predict the output targets, the target output of the XOR. And you see here now I plot the data in the initial, in the input space. You see that there is no way to do a linear classification, but then in the latent space, which is basically, the output space of the first layer, Z1 and Z2, you see that the two false results, they get mapped to the same point. And so now basically, the perceptron you can do with a linear perceptron, you can do a binary classification. And that's basically, the power of a deep perceptron and in general of deep neural network. Okay, this is it. Thank you. Bye-bye.